Okay, so we're going to wrap up our chapter on trig applications with a very common application or formula that's used in many applications, and that's called simple harmonic motion. And so we have one basic formula for simple harmonic motion, and that's as much exposure as I'm choosing to give you in this chapter. The chapter goes beyond the simple to dampened motions and other things, but I feel like it's better when you're getting into applications that you have something directly available for you to apply it, or else you won't remember it. So at least we have the exposure to harmonic motion, and we're going to use it in the fundamental basic formula. And it's, you notice it's either cosine or sine, and as we go through these problems we'll look at when would you use cosine and when would you use sine, and I'll point that out as we go. So let's go with the first one. Before we do that, let's remember that A equals is amplitude, but it can be positive or negative. So amplitude can be positive or negative. Sorry, A can be positive or negative. Amplitude is positive. So when it asks you, there you go, the absolute value of A is amplitude, and omega is in our formula for period. So that's not really omega, it's actually, our period is T equals 2 pi over omega, which is the period. And maybe something that we haven't been doing in the past, the last one is frequency is equal to 1 over T. Okay, so let's move on to the problems and see what we can do. So type the equation in the form of, so we're going to do A sine omega x instead of T. So we're going to use amplitude of 6 and a period of 1. So as we were just talking about, that A is going to be positive or negative, so we move down to the choice B. There are two equations, and when A is less than 0, y equals, I guess y is going to be negative 6 cosine, let's see, so what do we decide? Sine function. So sine function, sine omega is, so period is 1, so we need to find what omega is. Omega equals, let me start over again, T equals 1 equals 2 pi over omega, so omega equals 2 pi. So then we have sine 2 pi times x. I keep wanting to write t, but that's x in this case. So there we have it. That's the negative, and then when it's positive, y equals 6 sine 2 pi x. Okay, so just the positive and the negative on the little a. Now let's decide whether this is true or not. If the distance d of an object from its rest position at time t is given by a sinusoidal graph, the motion of the object is simple harmonic motion. So let's look at our choices. So this is not true. It's sometimes a damped motion, but not always. It is true, but not every motion given by a sinusoidal graph is simple harmonic. So it's not false. We've established that it's true, and this last reason was the theorem of simple harmonic motion states that an object that moves on a coordinate axis so that the distance d from its rest position at time t is d equals a cosine omega t, or d equals a sine omega t, where a and omega are greater than 0. So this is actually the definition of our simple harmonic motion theorem, so the answer is D. Okay, so now let's try it out. Excuse me, my dog is here, so you need to leave. Yes, I need to do this. Shh. Okay, let's see if we can do this without getting interrupted. An object attached to a coiled spring is pulled down a distance a from its rest position and then released. Assuming the motion is simple harmonic with a period of t, write the function that relates the displacement d of the object from rest after t seconds, and assume that the positive direction of motion is up. So the starting point is going to be when the object is in the negative position. So we're going to write, let's just write this. So let's find t. If t equals 2 seconds equals 2 pi over omega, then, omega equals pi. Why do I know that? Omega equals 2 pi divided by 2. So now we can write, and this is it's in the maximum position, and this is where we describe whether it's cosine or sine. So cosine, max displacement. Why? Because cosine at times maximum would be at 0, which is what time would equal to 0. So if we're looking at starting time equals 0 at the resting position, you would use sine, and if you're looking at the maximum displacement, you'll use the cosine. So we'll go down to B, and we will say amplitude is 5, and we're going to be in the negative direction because we pulled it down. And so then omega is pi, so it's cosine of pi times t. So we have amplitude of 5 in the negative direction, so negative 5, and we're using cosine because we're at maximum displacement, and we've determined that omega was pi. Okay, so let's see, we've got a similar object attached to a coiled spring in the down direction, A, from its rest position, and then released. Assuming the motion is simple harmonic with period t, we're going to write the function that relates the displacement to t after t seconds. And positive direction is up. So same as we did before. Let's first of all find out what omega is. So t equals 2 pi over omega. And so in this case, omega equals 2 pi divided by the t, which was 5 pi, equals 2 over 5. So omega equals 2/5. The amplitude is 8, and we're starting in the negative direction, so we'll use the cosine again. Negative 8, and then the omega is 2/5 times t. There we have it. Not too complicated. Now let's look at another one where an object is, same thing, is pulled down 6 units from rest and then released, assuming the motion is simple harmonic, period of 3, t equals 3. And now we have something different. Time at t0 is at the resting position and moving down. So here we have negative direction is 6. Okay, so we're still going to use the negative 6, but this time we're going to use the sine function because we're looking at time equals 0. We're going to be at the resting position, passing through it on our way down. So then let's find out what's next. Omega. We need omega. So t equals 3 equals 2 pi over omega. So omega equals 2 pi over 3. So we're going to do this, and we're going to go in the negative 6 direction, and 2 pi over 3 times time. All right, so there's the first 5. Let me find number 6. I'm out of order here. There we go. Now it looks like a lot of questions, but they go fairly quickly. So we have the displacement formula, d equals 9 sine of 10t, and yes, so no, oh yes, we do have meters, so you have units, meters, and seconds. So let's look at that as we go. Wait for it to focus. Does that sometimes. Okay, so is it simple harmonic? Yes, because it's in the equation form a sine omega t. These, by the way, you're not exposed to them because they have to do with the dampening motion. So hold that for another day. All right, so let's keep it here in focus. What is the maximum displacement from resting position? Well, the amplitude is 9. And we're looking at, if you go down a little bit to the way this is, yours is in a drop-down menu. Mine would say it's 9 meters. I don't really need the options there to figure this out, and I don't think you do either. What is the time required for one oscillation? Okay, so one oscillation would be 1 period. So let's see. So T equals T equals 2 pi over 10, because that's the omega. And so T equals pi over 5. And that is in seconds. So one cycle or oscillation is pi over 5 seconds. And then what is the frequency? Well, frequency equals 1 over t. So the inverse of that is 5 over pi. And what are the units? Well, this was seconds, so this is units per second, and there's no metric here, so it's an oscillation. So it's an oscillation per second. So spelling out oscillation per second, which is the wave frequency is measured. Okay, so let's do that again for number 7. Let's see what our numbers are. Now we have d equals 8 cosine 2 pi t. So before I begin, I would like to go ahead and get my t. So t equals 2 pi over omega, which is 2 pi. So t equals 1. And second, by the way. So I just do that first, but I'm sure it's going to be coming up quickly in the questions. So is this simple harmonic motion? Yes, it's got the right equation, so D. What is the maximum displacement? That's going to be the coefficient A, so that would be 8, and we're measuring in meters. And the time required for one oscillation is 1 second. I did that calculation. And the inverse of 1 is 1 oscillation per second. So if it takes 1 second to go through an oscillation, it's 1 oscillation per second. Let me pull all that up so you can see all of that. Okay, let's look at number 8. All right, so we have a formula already given to us, and we're going to again go through the same steps. I'm going to find my t first because I like to do that. So t equals 2 pi over omega, which is 1/7. So if I multiply through by 7 over 7, I cancel these out, and I get 14 pi. So t equals 14 pi seconds. So yes, it's simple harmonics because I didn't give you any other kind of problems. Let's go on. The maximum displacement is the coefficient, so it's 5, and it's measured in meters. And the time required for one oscillation was 14 pi seconds, which makes the frequency 1 over that, 1 over 14 pi, and this is an oscillations question, so oscillations per second. And you can see all the choices will be drop-down menus. Okay, so let's look at our last problem now. Maybe get a little bit more exciting, probably not. Okay, we have a loudspeaker oscillating with the equation of the cosine, and we have 532 hertz, and that's something you'll sound familiar to you. That means cycles per second. Maximum displacement of 1.2. So A equals 1.2 millimeters, and F equals 532 cycles per second, which means T equals 1 over 532 seconds. What else do we need to know? Omega. So let's find, so T equals 1 over 532 equals 2 pi over omega. So omega equals, multiply through there, 532 times 2 is our hardest thing we've done so far today. I'm just going to double it at 1064 pi. All right, so then let's see if we can find the formula that fits that. And it is cosine, so we're going to use the cosines. They're all cosines. The coefficient is 1.2. Good, and so we'll eliminate these guys. And we will go with 1.2, eliminate that one too. And here's the one with the correct omega, 1064 pi t. So our formula is D equals 1.20 cosine 1064 pi times t. And that's it. Those are all the problems I wanted you to work for simple harmonic motion.